Okay, welcome everybody. Today we're going to talk about pre-calc lesson number 22. We're still talking about section 2.6, and today we're going to focus on discontinuities. So I know we talked briefly about these earlier in the chapter, but we're really going to kind of drive home the point here. Just to kind of, again, set up a little bit about why we're doing section 2.6 this way with the worksheets and whatnot. I'm actually showing you guys rational functions in a completely different way than I would have last year, focusing on the theory behind it as opposed to the actual graphing. I do think that is going to be more beneficial to you next year, as the idea of rational functions and discontinuities is one of the most important topics in calculus. So in some ways, I actually think these lessons are a little too lengthy, meaning that they're really a little bit repetitive. You probably could understand the point in half the time. But the truth is, because it's so important, there really is no downside to just making sure you understand exactly how everything is connected. So that's why it's worth spending a little bit of extra time. So just to kind of set the scene here, there are two major types of discontinuities in functions. Again, we had talked about these briefly last week. So if you realize in general that there is a discontinuity in a function, you're going to first separate them into two different categories. Discontinuities that are removable, which as far as we're concerned, those are the good ones because you could potentially fix them, versus non-removable, which we're going to consider the bad ones because you can't fix them. You would then call a removable discontinuity a point discontinuity, and you would actually find that point. An infinite discontinuity is one type of non-removable, and a jump discontinuity is the other type of non-removable. So a couple of other things we want to add in here. So just to remember what it actually means to be a discontinuity. So a discontinuity, these are breaks in a graph. It's basically any location that forces the graph to not be continuous. So again, you're separating all of your discontinuities essentially into two categories, those that are removable and those that are non-removable. And then you can either be a point discontinuity, which again, just to clarify, you're actually going to find a point, whereas for infinite and jump, you're just going to tell me where. And then another little note here about a jump discontinuity is that these only occur in piecewise functions. So now that you kind of have a little visual here of what's happening in terms of discontinuities, let's go ahead and talk a little bit more about what is actually happening at the graph there. So when you're talking about a point discontinuity, what you're actually saying here is that the two pieces are connected at an open circle because they approach the same y value. So yes, it's easy to recognize, I think, where the point discontinuity is, but if you were looking to describe them, there are again two pieces that connect at an open circle because they approach the same y value. Whereas if you're talking about an infinite discontinuity, you would describe this as being two pieces that don't connect because they approach positive or negative infinity. And we'll say plus or minus infinity. And then finally, for the jump, you would write this as two pieces that don't connect because they approach different y values. So as I've been trying to kind of reiterate over the last couple of lessons here, it's not just as important that you can actually calculate, for example, where the point discontinuity is, but it's important that you're also able to describe what is actually happening here. So give everybody a second to kind of copy that down. And again, you should now have a visual. You're assuming that every function starts with an idea of being continuous from negative infinity to infinity. Once you realize that there is in fact a break in the graph, that's how you know that you have a discontinuity. You would then have to kind of train your brain to start thinking about, well, is it removable or non-removable? If it's removable, how do I actually find the point and what does it mean? Whereas if it's non-removable, which of the two, infinite versus jump, is it? And then again, how do I find it? So let's take a look at these examples below here. So if you take a look at the left side, the graph below has a removable point discontinuity at x equals 1. And then the one in the middle, there is a non-removable infinite at x equals 1. And then for the last one, there's a non-removable jump at x equals 1. So again, just to highlight, we're talking about this open circle versus this vertical asymptote versus the fact that these two pieces don't meet. So those are all discontinuities. And discontinuities affect always the domain and then sometimes the range. So you kind of have to do the range on a case-by-case basis. So for the domains, if you remember what we did last lesson, the domain is always all real numbers except where the discontinuities are. So the fact that in all these cases, the discontinuity is at 1 means that the domain of each of these is going to be everything except for 1. And then the range, you have to actually look at the graph and go on a case-by-case basis. So again, sometimes it's going to be all real numbers if there are no breaks, and then sometimes it's going to vary from case to case. So if you're looking at the graph all the way to the left, remember that the range is y values. So because of the fact that this piece goes to negative infinity and this piece goes to positive infinity, every single y value along the way is in fact accounted for, which is going to be an all real number situation. For the piece in the middle, even though you have these two separate branches, each of the branches is going all the way up and all the way down. So again, that's an all real numbers situation. If you take a look at the third piece, because the piece on the left is going all the way up and because the piece on the right is going all the way down, this is actually going to encompass all the real numbers as well. But just to be clear, that is not always going to be the case. Please don't just think that because these three have ranges of all real numbers that all of them will, because that certainly is not the case. While you can use the domain negative infinity to infinity, except for the discontinuities, for the range, you really do have to look at it at a case-by-case basis. So now that we've talked about these discontinuities, let's talk a little bit more about how we would find them. So if you take a look at the next page of your notes here, notice that you have 4 different equations and 4 different graphs. We're going to start by looking at their pictures, and then we're going to kind of work backwards and talk about where the values on the graph come from. So notice that for each of these graphs, there is a point discontinuity. We can see it not only on the graph, but we can also see the coordinates of it. Remember, in the future, when you're asked to find a point discontinuity, you have to actually find the entire point. So in the top left graph here is my non-removable point discontinuity, and that is at the location 3,7/5. And again, you do have to find the whole coordinate. Compare that to the top right. So my removable point discontinuity would be at -3, positive 1/2. Again, kind of the nice reason why we're doing these worksheets is because you really do need to see the immediate connection between the equation and the graph. Then the 2 on the bottom, so your coordinate for graph number 3 would be -2, 1, where your coordinate for the final one would be -2, -1. And again, we're going to go ahead and just highlight all those point discontinuities. So now we're going to go ahead and kind of work backwards. We're going to look at each of the equations, and then we're going to decide how is it that we got those graphs and how is it that we got those discontinuities. And of course, if you're taking a look at each graph, in addition to having those points, notice that each of those graphs also has a vertical asymptote. So of course, that is where our infinite discontinuities are going to be. So we're going to go ahead and look at those as well. Something to point out here, none of these graphs start off as piecewise functions, so we're not going to have any jump discontinuities when it comes to rational functions. We've seen some jump discontinuities in the past, and we'll certainly see them in the future, but we're not going to see them today other than just talking about the fact that they exist. So now if we go ahead and look at the table on the next page, notice that you again have all 4 functions on the left-hand side. Then you have 5 different columns that we're going to go ahead and fill in. And the first column is asking you to rewrite the function in completely factored form. So I'm going to give you a second to go ahead and pause and try it. Go ahead and make sure that you can, in fact, factor each of these 4 equations. The majority of the factoring is simple, but there are some that require either the AC method or, again, whatever strategy you happen to use. So go ahead and pause and try it, and please try to factor completely each of these 4 rational functions. So go ahead and do that. All right, so hopefully you had a chance to pause and try it. And so now double check and make sure that all your answers are correct. And again, it's really only in the first one and the last one in the numerators that when you have a coefficient of 2, that you would have had to either do the AC method or some other kind of fancy factoring, as opposed to just finding 2 factors of the last term that add up to be the middle term. In case you haven't realized, it is very, very, very important that you are able to factor quickly and accurately. So that should really be your main goal before you even try to do any of the rest of this. You should make sure that you, in fact, can factor. So now that you have factored, you're going to go ahead and identify the restricted values of the functions. Whoops, sorry about that. Go ahead and erase. So you're going to go ahead and find the restricted values of the function. And again, the restricted values at this point come anywhere from the denominator. So if you take a look at the denominator in the first example, your restricted values are the fact that x cannot equal 3 or negative 2, compared to the next one where x cannot equal negative 3 or 1, x cannot equal negative 3 or negative 2, and then x cannot equal negative 3 or negative 2. That drives home the point of what we did yesterday, reiterating the fact that any restriction, any discontinuity, as it were, comes from the denominator. What we're going to go ahead and do now is we're going to rewrite the function from the first column into simplified form. So rewriting it into simplified form means that if there are any common factors, which there clearly are, we're going to go ahead and essentially cancel them out. So in the first example, you'd be canceling out the x minus 3s, canceling out the x plus 3s, canceling out the x plus 2s, and then canceling out the x plus 2s. So we're going to go ahead and rewrite them in simplified form. So these would all be f of x equals, and again, I probably won't write it every time just to save myself some room. So 2x plus 1 over x plus 2 compared to x plus 1 over x minus 1 over x plus 3, and then 2x plus 3 over x plus 3. And again, these should all still be f of x equals. I just don't really have enough room in my box, so feel free to write that for yourself. What you have here in the third column is still the f of x function, but it's now just a simplified version. I think in the past, perhaps last year, you would take the first column, literally cancel out the common factor, and then just never even go back and think about what the original problem looked like. I think it is very important that you're able to look at both of those. What does it look like in its factored form versus what does it look like in its simplified form? So now that we have factored and reduced, now we're going to go ahead and take each of these restricted values that we found in the second column, and we're going to go ahead and get specific and classify them in terms of what kind of discontinuity they are. So notice that in column number 4, it asks you for the factor that cancels out. So if you're talking about the factor that cancels out, we're talking about x minus 3 in the first case. We're talking about x plus 3 in the second case. We're talking about x plus 2 in the third case. And we're talking about x plus 2 in the fourth case. If from this point forward, you have a factor that cancels out, that is always going to be a removable point discontinuity at whatever value of x would make that factor 0. So if you were to set the factor equal to 0 and then solve, you would get x equals 3 in the first case. You're going to get, again, a removable point discontinuity at x equals negative 3 for the second example. You're going to get a removable point discontinuity at x equals negative 2. And then you're going to get a removable point discontinuity at x equals negative 2. So again, every time you have a factor that cancels out, that is always where your removable point discontinuities are going to be located. Whereas in the final column, if you're talking about a factor that does not cancel out, again, and both of these are of the denominator, or in this case, you're talking about the denominator. So what factor does not cancel out of the denominator? So in example number 1, or in each of those examples, it's the non-highlighted factor. So that would be x plus 2 versus x minus 1 versus x plus 3 versus x plus 3. Whenever you have a factor of the denominator that does not cancel, you are always going to get a non-removable, NR, infinite discontinuity at, again, whatever value of x would make that factor 0. So -2 for the first one. Non-removable infinite discontinuity at +1. Non-removable infinite discontinuity at -3, and non-removable infinite discontinuity at x equals -3. And again, perhaps it's possible that I could have shown you just one of these examples and you would have gotten the idea of how do you know how to simplify? How do you know where the point discontinuity is versus how do you know where the infinite is? But honestly, it's worth doing 4 examples compared to 1 so that you're positive exactly where each of these things comes from. So from this table, we now have one additional thing that we need to do. As I mentioned, when it comes to point discontinuities, you have to find not only where the x value is, but you also have to be able to tell me the coordinate of that point discontinuity, because we care about the y value because sometimes there's an effect on the range. So let's go ahead and take a look at the final page of our notes here. And so notice we have another table, and then we also have some summaries that we're going to do. So at the top here, based on the information in the previous page, what can you say about the discontinuities? So we're just going to go ahead and summarize everything that we found so far. So discontinuities occur at restricted values of the rational function. So that's the main idea, making sure you understand that discontinuities are a thing and they happen anywhere that there's a restriction. Then once you realize that there is going to be a discontinuity, you're going to make sure you understand the difference. So removable point discontinuities occur at restricted values whose factors cancel out So bottom line, removable point discontinuities happen at the places where the factors cancel out, compared to the third conclusion where non-removable infinite discontinuities. And again, those are your vertical asymptotes. We're going to start calling them more vertical asymptotes in the next few lessons when we actually go ahead and start graphing them. Occur at restricted values whose factors do not cancel out. Of the denominator. So again, if you're looking to just kind of give that a summary, non-removable infinite discontinuities, also known as vertical asymptotes, those occur at the restricted values whose factors do not cancel out, and again, has to be talking about the denominator. Remember yesterday, we went through a whole exploration of what happens if you have factors that are in the numerator, so you do have to be able to differentiate. So give everybody a second to make sure that you're writing that all down, and then we'll go ahead and fill out this table. And then notice that these are the same 4 functions we've been talking about all day, but we're just going to go ahead and again now take it one step farther. So the function on the very left-hand column, rewrite them in simplified form. We already found those simplified forms, so we're just going to go ahead and rewrite them again. And again, they all should be f of x equals. I'm just going to write it once at the top to give myself a little bit of extra room. So let's go ahead and rewrite all those functions. from the previous problem. And again, this is what you would be left with if you went ahead and canceled out that common factor. So then at what value does the graph have a point discontinuity? That would have happened from the canceled factor. So if we refer back to the previous page, the canceled factor that would have happened in the first one would have meant that there was a restriction at 3 versus the restriction at -3 versus the restriction at -2 for the final two. And again, all you have to do is refer back to the previous page if you want to actually see where was the factor that canceled. So now that you have identified what the simplified form is, now that you are 100% sure at what value of x is there a discontinuity, you're going to find the value of the simplified form for that x value. So that means that you're going to take your simplified version, which is here in the second column, and you're going to plug in the values from the column that are next to it. So that means that you are going to essentially be finding f of 3. So if you're plugging that into the reduced form, 2 times 3 plus 1 over 3 plus 2, that looks like 7/5. And the ultimate conclusion is that that is the actual coordinate of the whole, 3, 7/5. And if you were to go back to page 2 and look at the graph of this first function, you would exactly see that that is where the point discontinuity is. So the conclusion that we're ultimately trying to gain here is that when you have a point discontinuity, it comes from when you cancel out a common factor, take that value of x that's restricted and plug it into the simplified version. So g of -3, if we plug that into our reduced form, we get -3 plus 1 over -3 minus 1. That's going to go ahead and give us -2 over -4, which means that my coordinate is going to be -3 1/2. You should go ahead and pause and try it and try to do the last two. See if you can plug in the restricted value and see if you can find the entire coordinate of the whole. All right, so hopefully you have tried every single one now, and you have the final conclusion here for the last column of how you actually find the entire coordinate of the whole, which again means the removable point discontinuity. Looking at the bottom here, it's just summarizing what you did in terms of finding the whole. So if you're trying to find the whole in the graph, which again, all these terms are going to be used interchangeably, so you have to know all of them. Just to reiterate the point, how do you find the x value of the whole? It's the restricted value that comes from the canceled factor. And then once you identify what that restricted value is, how do you find the y coordinate? You're going to plug, the x, and that's the x from the previous step, into the simplified function. And emphasis here on the fact that you have to plug it into the simplified version, because if you don't plug it into the simplified version, you're going to get 0 over 0, and that's not going to help you one single bit. So again, I probably could have done this lesson with half the examples in half the time, but I really see no downside to just really trying to drill into you exactly what the different kinds of discontinuities are and how to specifically find them. So you're going to go ahead and do homework 22 tonight, which again is a worksheet. We will have a couple more lessons next week on these different types of rational functions, and then we will get to the actual graphing soon. So thanks very much for tuning in, guys, and we will catch you next time.